Have you ever wondered what polymorphism is and how it impacts our lives? Well, let's dive right in. Polymorphism in the world of material science refers to the ability of a solid material to exist in more than one form or crystal structure. Imagine a chameleon, how it changes its color based on its surroundings. That's nature's version of polymorphism. In a more concrete sense, polymorphism allows substances to take on different physical properties while maintaining the same chemical composition. This makes it an intriguing subject of study, especially in the pharmaceutical industry. Because believe it or not, the way a medicine is crystallized can impact how effective it is in treating a condition. So when you pop that pill for a headache or sip on that soothing cough syrup, there's a good chance polymorphism played a part in its development. So, polymorphism isn't just a scientific term, it's a phenomenon that has significant implications in our lives. Now that we know what polymorphism is, what about the different shapes or forms it can take? Well, let's dive right into that. Polymorphs, by definition, are the same substance existing in more than one crystal form. These forms, or shapes, can change based on different environmental factors, such as temperature and pressure. Imagine a chameleon, a creature known for its ability to change its skin color based on its surroundings. Polymorphs are the chameleons of the chemical world, altering their shapes in response to changes in their environment. Let's start with temperature. As one of the key factors, temperature can greatly influence the formation of different polymorphs. Think of it like water. At low temperatures, it freezes into solid ice. Increase the temperature and it melts into liquid water. Crank up the heat even more and it vaporizes into steam. Similarly, a substance can transform into different polymorphic forms at different temperatures. Now, let's talk about pressure. Just as deep-sea creatures adapt to high pressures by developing unique shapes, substances under high pressures can form different polymorphs. A diamond, for instance, is a high-pressure polymorph of carbon. In contrast, graphite, the stuff in your pencil lead, is a low-pressure polymorph. Other conditions such as the rate of cooling, the presence of impurities, and mechanical stress can also influence the formation of polymorphs. It's a fascinating interplay of conditions that result in these diverse shapes. In the realm of pharmaceuticals, understanding these different shapes is crucial. Each polymorph of a drug can have different physical properties like solubility and stability, which can significantly affect the drug's performance. That's why pharmaceutical companies invest a lot of time and resources into studying and controlling polymorphism. As you can see, polymorphs can take on a variety of shapes based on their environmental conditions. And that's just the tip of the iceberg. The world of polymorphs is as vast and varied as the shapes they can take. So stick around as we delve deeper into this fascinating topic in our next segment. Wondering how polymorphism applies to the pharmaceutical industry? Well, let's delve right into it. Polymorphism in pharmaceutical terms refers to the ability of a solid material to exist in more than one form or crystal structure. These different forms are known as polymorphs. Polymorphs, despite having the same chemical composition, can exhibit different physical properties such as solubility, melting point, density, and even color. And it's these differences that can significantly affect the performance of a drug. Take the case of ritonavir, an antiretroviral drug used in the treatment of HIV. It was released in the late 90s with a certain polymorph, but then a more stable, less soluble polymorph of ritonavir emerged, leading to a decrease in its bioavailability. The new form was less effective at delivering the drug into the body, causing a significant disruption in treatment plans for many patients. Then there's the case of the anti-ulcer medication, ranitidine hydrochloride. It has two polymorphs. One is needle-shaped and the other is more block-like. The needle-shaped form tends to clump together, making it hard to manufacture into a pill. The block-like form, on the other hand, is easier to work with and results in a more effective pill. And it's not just about the efficacy of the drugs. Polymorphism can also affect the drug's stability. For instance, certain polymorphs may be more prone to degradation, which could reduce the shelf life of the drug. This is why understanding and controlling polymorphism is so crucial in drug development. So, how does the pharmaceutical industry use polymorphism? Well, during the drug design and development process, researchers will often try to identify the most stable and effective polymorph of a drug. This involves using various techniques to induce and study the formation of different polymorphs. Moreover, polymorphism can also be used to improve existing drugs. By finding a new polymorph, researchers can increase a drug's solubility and hence its bioavailability. This can lead to the development of a more effective version of the drug. In addition, understanding polymorphism can help in addressing issues related to patenting and intellectual property rights. Different polymorphs of a drug can be patented separately, allowing for extended market exclusivity. However, this can also lead to legal disputes, as seen in the case of the antidepressant Paxil, where a battle over the patent of a specific polymorph ensued. Clearly, polymorphism plays a crucial role in the development and effectiveness of pharmaceuticals. Its understanding is vital for the pharmaceutical industry, from the initial stages of drug design and development through to manufacturing, patenting, and even in improving existing medications. So the next time you pop a pill, remember, there's a lot more to it than meets the eye. But how do scientists detect these polymorphs? Well, let's dive into the fascinating world of detection techniques. These methods are not only intriguing, but they also play a crucial role in identifying polymorphs and furthering our understanding of polymorphism. One of the most common techniques is X-ray diffraction. This is where X-rays are shot at a crystalline material and the resulting pattern of scattered rays is studied. By analyzing this diffraction pattern, scientists can decipher the arrangement of atoms within the crystal, thus identifying its polymorphic form. It's a bit like solving a three-dimensional jigsaw puzzle, isn't it? Then we have infrared spectroscopy, another powerful technique. Here, infrared radiation is passed through a sample, and the absorption of specific wavelengths allows us to identify different chemical bonds. Since polymorphs have different arrangements of molecules, they will absorb infrared radiation in slightly different ways, allowing us to distinguish between them. Think of it as a unique fingerprint for each polymorph. Finally, we have thermal analysis, which includes methods like differential scanning, calorimetry, and thermogravimetric analysis. In these methods, changes in physical and chemical properties are measured as a function of increasing temperature. Each polymorph has a unique thermal signature, and by studying these signatures, scientists can identify which form of a substance they're dealing with. Now, these are just a few examples of the techniques used to detect polymorphs. There are many other methods out there, each with its own set of advantages and limitations. The choice of method often depends on the nature of the substance being studied, the equipment available, and the specific information required. In a nutshell, detection techniques are the eyes through which scientists explore the intricate world of polymorphism. They allow us to delve into the microscopic world and understand the different forms that substances can take. Without these techniques, our understanding of polymorphism would be like trying to navigate a maze in the dark. These detection techniques are vital tools in the study and application of polymorphism. And with that, our journey through detection techniques comes to an end. But stay tuned because we're about to dive into the fascinating concept of glass transition temperature. And what does glass transition temperature have to do with all of this? Well, the glass transition temperature, or TG, is a pivotal concept in understanding polymorphism. Just like the name suggests, it's the temperature at which a polymer changes from a brittle, glassy state to a more flexible, rubbery one. But here's the kicker. The glass transition temperature is not a fixed point but a range, and it's highly dependent on the rate of heating or cooling. So, how does this tie in with polymorphism? You see, different polymorphs of a substance can have different glass transition temperatures. This impacts the stability of the polymorphs, especially in pharmaceutical applications. For instance, a polymorph with a higher TG will be more stable at room temperature, which can be crucial when it comes to drug shelf life. Moreover, the TG can also affect the properties of the polymorphs. A lower TG might make a polymorph more soluble, enhancing its bioavailability. Conversely, a higher TEG could lead to a more durable product, which is desirable in applications like tablet manufacturing. Remember, the glass transition temperature isn't just a number, it's a critical factor that influences the behavior of polymorphs, playing a significant role in their formation, stability, and properties. So the glass transition temperature is another key factor in the fascinating world of polymorphism. So, we've explored the intriguing world of polymorphism and its applications. We've seen how different shapes of polymorphs can greatly impact their properties and uses. We've delved into its profound implications in the pharmaceutical industry, and even touched on detection techniques and the concept of glass transition temperature. It's clear that polymorphism is not just a scientific curiosity, but a critical factor in our everyday lives. Subscribe for more, because you won't find me later. Dive deeper into the world of science with us.